share it. Let me contact to next person. Okay. So have you any doubt regarding previous lecture?
No.
Yes or no?
No.
Okay, wait a minute. Have you come? Okay, we didn't start flame coloration yet. So today's new topic is flame coloration. Right topic, flame coloration. Actually, whenever there is a flame on S block elements, they imparts color, different color. And some of the elements from S block do not show any color due to its high ionization enthalpy. Or actually we can say that the energy or the heat energy from flame is not enough to excite its electron. That's why it doesn't impart any color. What is flame coloration? Basically, whenever a flame is or a heat is given to elements from S block element, the electron gets energetic and move to the higher energy level. And then again, when it's lose energy, it de-excite. This is called excitation from lower energy to higher energy, and this is called de-excitation from higher energy to lower energy. This is de-excitation, and it releases some radiation, and that radiation basically, with respect to that radiation, there is some wavelength which falls in visible region that we are able to see different colors according to the uh, wavelength, according to the size of the wavelength. So I'm going to write a point here. Energy is released in terms of radiation, in terms of radiation. So I'm going to write a point regarding alkali metal. So write with me. Alkali metal imparts characteristic color to the flame due to low ionization energy. Do you know what is ionization energy?
Energy required to form ions.
Yes, energy required to remove an electron, that is called ionization energy. Alkali metal imparts characteristic color to the flame due to low ionization energy. Its valence electron gets excited, and during de-excitation, that means coming from higher energy to lower energy, during de-excitation, energy is released. Energy is released in terms of or in form of radiation lying in visible region, lying in visible region. So that's why it imparts color, or it shows different colors. Different elements shows different colors. Just write it, and then I'll tell you which element shows which color during flame.
Done.
Done. Very good. Okay, here are some colors. Lithium source, crimson red. I'm going to write it from red color. Crimson red. Sodium, potassium, rubidium, and then cesium. Yellow or golden yellow. This is basically violet. This is basically red violet. Cesium shows blue color. That means alkali metals, all the alkali metals shows flame coloration. But when we come to alkaline earth metal, here in alkali earth metal, beryllium and magnesium do not show flame coloration. Why they do not show? Because the ionization of energy of beryllium and magnesium is high due to its small size, so it doesn't get enough energy from flame to excite its electrons. Okay, are you getting my point?
Yes.
Now I'm going to write the reason. Because beryllium and magnesium have higher ionization energy, due to which amount of energy required to excite the electron is not enough from the flame. So it's so easy to understand why it doesn't impart any color or why it doesn't show flame coloration.
Done.
Very good. Since we have completed physical properties, now we will start chemical properties of S block. Chemical properties of S block. So start writing with me. S block metals are highly reactive because their size is very high as compared to other groups. Their size is very large as compared to other groups. So its electron can easily be donated or its electron can come out from their shell. That's why they are very highly reactive. Due to low ionization energy. Due to low ionization energy. Next point we can write alkali metal is highly reactive than alkaline earth metal, that because first group is larger than second group. Alkali metal is highly reactive than alkali earth metal due to lower ionization energy of alkali metal. And why it has lower ionization energy? Because its size are larger than alkaline earth metal. So if we are going to arrange lithium, sodium, potassium, rubidium, cesium in increasing order of reactivity, either this or second group, beryllium, magnesium, calcium, strontium, barium. We don't talk about francium from the first group and radium from the second group because they are radioactive element. So, are you getting my point?
Yes.
You can see lithium is smaller than sodium, and the larger atom from larger elements from first group is cesium. So its ionization energy will be very lower. That's why it can easily donate its electron, and that's why it is highly reactive. In this order they will be arranged, right?
Yes.
This is the arrangement of reactivity. Just write it and let me know. So when will your be final paper?
Um, chemistry is on 27th March.
Is this your final paper?
Yes.
Oh, okay.
It will start from 17th March. Chemistry is on 27th March.
I thought in this month it is.
Oh,
That means we have time. I thought
yes.
it's 27th Feb. Can I change the slide, or are you done with this?
Yes, done.
Okay. Now we will start reactivity towards different things like elements: hydrogen, water, oxygen, air. So first write reactivity towards hydrogen. So basically reactivity towards hydrogen, what it is, alkali metal reacts with hydrogen to form ionic compound. Alkali metal react with hydrogen to form ionic compound. You know that this is alkali metal M and this is hydrogen. It has a valency 1 as well as this has also valency 1. So if they will combine, they will form a compound MH. We taught about this in class 9th, crisscross. Do you remember? So we are going to take 2M that react with hydrogen, is not found in elemental form. So it founds in form of dihydrogen. So the compound will be 2MH, or we can write Li plus H2 will give LiH, and for balancing we are going to multiply it by 2. In the same way, sodium, if sodium reacts with dihydrogen, it will form NaH, or for the balancing we are going to multiply it by 2, right?
Yes.
So just write it.
Done.
Very good. Now write a topic: thermal stability, which is very important topic. Thermal stability. Whenever there will be question regarding thermal stability, which one has greater thermal stability, lower thermal stability, or arrange in increasing or decreasing order of thermal stability, you have to look on a compound and uh, find out whether it is covalent compound or ionic compound. Can you recognize whether it is covalent? If a compound is given, like if I'm giving you NaCl, is it covalent or ionic?
Ionic.
Ionic compound. So first of all, you are going to check the compound whether it is covalent or ionic. Okay. Now the second, first you are going to check it. If it is covalent, then thermal stability directly proportional to bond energy. Do you know how to calculate bond energy? Which one will have more bond energy and which one will have a stronger bond energy? Always remember, bond energy or bond enthalpy inversely proportional to bond length, and bond length that depends upon the size of atom. If the size of atom is smaller, that means bond length is smaller, and if the bond length is smaller, that means bond energy is high. That needs a lot of energy to break the bond. Is that clear?
Yes.
Now, if the compound is covalent, you have to check the bond energy, and then bond energy directly proportional to thermal stability. So you can easily arrange that in order of thermal stability. And if the compound is ionic compound, if the compound is ionic compound, you have to look in the ionic compound and you have to search whether it has a smaller anion or larger anion, or you can say monoatomic anion or polyatomic anion. Polyatomic anion. Do you know what is polyatom?
More than one
What you just said?
atom. More than one atom.
Yes, more than one. Very good. Or that means polyatomic anion, monoatomic. That means only one anion, like O minus 2, N minus 3, F minus, like this. If the ionic compound has monoatomic anion, that means thermal stability directly proportional to lattice energy. We have to go through lattice energy. Do you know how to calculate, how to arrange compounds in lattice energy?
Mm.
See, lattice energy is directly proportional to magnitude of charge. Magnitude of charge. And lattice energy is inversely proportional to size of ion. So I'm going to take an example. Just suppose NaCl and MgCl2. Which one has more lattice energy? You are going to see chlorine is common. So go for sodium and magnesium. Sodium will have charge +1 and magnesium will have charge +2, right? And you can see lattice energy directly proportional to magnitude of charge. That means MgCl2 will have more lattice energy than NaCl, right?
Yes.
And if you are going for LiF and NaF, now you will see that both have same charge. This has +1, this has -1, this has +1, so this has -1. So we cannot compare by charge. So we are going to check its ionic size. So since fluorine is same, we are going for Li plus and Na plus. Which one has a smaller size?
Lithium.
Lithium. So if the lithium has a smaller size, lattice energy of lithium will be higher, right?
Yes.
So this will have more lattice energy. So in this way we calculate lattice energy, and if you are going to arrange in lattice energy, you can easily arrange it in thermal stability. And if there is polyatomic anion, what you have to do is, what is polyatomic anion? Like CO3 minus 2, SO4 minus 2, NO3 minus 2, like this, etc. Thermal stability depends on Fajan's rule. Thermal stability depends on Fajan's rule. More covalent character, less thermal stability. Do you know how to what is Fajan's rule?
No.
Basically, Fajan's rule, we studied in chemical bonding. Fajan's rule, according to Fajan's rule, none of the compound is 100% ionic and 100% covalent. None of the compound has 100% covalent character or 100% ionic character. There will be always some covalent character in ionic compound, and there will be always some ionic character in covalent compound. So basically, according to Fajan's rule, we we arrange ionic compounds in covalent character. We arrange ionic compound in covalent character, like which ionic compound will have more covalent character and which ionic compound will have less covalent character. I'm going to explain it. Just write it first, then we will. Done.
Almost.
So I'm going to explain Fajans rule first. Just see here what is Fajans rule. You know that HF is covalent compound, right?
Yes.
But you also know that fluorine is highly electronegative element, and fluorine is very electronegative element than hydrogen. So the electron of hydrogen, basically fluorine, will attract or withdraw electron from hydrogen towards itself, so it's slightly displaced from its place towards fluorine, and it got delta positive charge, and it will get delta positive charge, and it will get delta negative charge. Are you getting my point?
Yes.
And now see, uh, whenever we talk about positive and negative charge, only basically ionic compound forms by the attraction between positive and negative charge, right? Gain or loss of electron, and there will be positive and negative, and there will be electrostatic force of attraction, and the bond between them is called ionic compound. In the same way, you can see there is slightly positive and negative, that means there is some ionic character as well, right?
Yes.
In the same way, if we have NaCl, you can see Na plus and Cl minus, there will be force of attraction, no doubt. But at the same time, this is the cation we have, and this is the anion we have, right? Because we know that basically anion is larger than cation. Okay. Now see, this is anion and this is cation. This is cation, since it has more positive charge, so it will start attracting this fluorine towards itself, attracting this fluorine towards itself. And according to Fajans rule, it will attract so strongly that it will deform chlorine. What it will do, it will deform chlorine. That means it will look like that chlorine is going to overlap with sodium plus. So basically I can see say that like this is chlorine and this is fluorine, and it will attract so strongly that it will appear to go and overlap with that. That's why this has some covalent character as well. And now how we will measure that which one will be more covalent and which one will be less covalent? So basically according to Fajans rule, size of cations inversely proportional to polarization. Polarization. What is polarization? Basically, the power with which cation is attracting or cation is withdrawing anion, that power is called polarization. The size of cation will be smaller, it will have more power to polarize the anion. So size of cation is inversely proportional to polarization, and if there will be more polarization, or anion will be more polarized, that means polarization directly proportional to covalent character. Polarization directly proportional to covalent character. Like if I'm going to give you that question, it will be more clear. Like if I'm going to give you NaCl, NaBr, NaI, NaF. Now see what happens. If I'm going to ask you which one have more covalent character, you know which one have more covalent character? I just took all the things similar. Let me change my question. LIF or LICL? NaCl, KCl, RbCl, CsCl. Just arrange it in increasing or decreasing order of covalent character.
LiCl has most covalent character.
This is a wrong answer. Just think about it.
Cesium,
Yes,
Cl has
cesium
most.
has more covalent character because you can see in this anion have same, this anion is common, so we will go for cation Li plus, Na plus, K plus, Rb plus and Cs plus. Let me know which cation has larger size.
Cesium.
Cesium. Since cesium has larger size, that means the cesium will have minimum polarization power, and if there is minimum or less polarization power, that means covalent character is
More.
minimum or maximum.
Maximum.
How? The answer will be like this, because you can see you were correct earlier. I was just distracted. uh, LiCl, you can see smaller the size of cations, higher will be polarization power, and if higher will be polarization power, high it will have more covalent character, isn't it, Akifa?
Yes.
And if we are going to increase the size of cation, polarization power decreases, and if polarization power decreases, that means covalent character also decreases, right? Okay, can I change the slide?
One second.
Yes or no?
No, 1 second.
Okay, take your time. Done.
Done.
Very good. Now we have only one factor, size of cation. Now we will talk about can you tell me uh, the size of, just I will give you after this. Now charge on cation, charge on cation directly proportional to polarization. Charge on cation directly proportional to polarization, and polarization directly proportional to covalent character. So if you have given that NaCl, and here it is given that MgCl2, and here it is also given AlCl3. Since chlorine is same or common, you can go for charge Na plus cation Mg plus 2 and Al plus 3. Now you can see aluminum has more charge on cation, that means it has more polarization power, and if it has more polarization power, that means it is more covalent in character, covalent character, right?
Yes.
Just write it.
Done.
Done. Very good. Now we are going to see it in terms of anion. Okay. So charge on anion. Basically, anion is polarizable and cation has polarization power. Charge on anion is directly proportional to polarizability. Polarizability, which is directly proportional to covalent character. Since you can see that this is a cation and this is an anion, and this is the same cation and this is another anion. This anion has -1 charge and this anion has -2 charge, which can be easily polarized. This one, because it has more electron density, so it will have some repulsion between itself, uh, between itself's electron, and they can easily be attracted, right?
Yes.
So basically that's why charge on an ion is directly proportional to polarization, and that's why polarizability, and if it will be polarized easily, that means it has more covalent character. Also, size of an ion directly proportional to polarizability, which is directly proportional to covalent character. Now you can easily see same cation. I am taking same cation, one with one, the energy is bigger than the previous one. Now you can see the electron which it attracts will be from its valence electron. So you can see that there will be nucleus in cation anion also. So force of attraction here will be maximum because the distance between electron and nucleus is lesser, and here the force of attraction is lesser because the distance between nucleus and its electron is larger. That's why force of attraction decreases. So it will be more easy to attract an anion from larger size than a smaller size.
Yes.
So that's why it is directly proportional to covalent character. This is all about Fajan's rule. On this base, we just decide which one has a more covalent character, which one has lesser covalent character. The one which has more covalent character will have lesser thermal stability. Generally, ionic compound has more thermal stability than covalent character. Sorry, than covalent compound. Are you done with this?
Yes.
Okay. Thermal stability of hydride. I'm going to talk about thermal stability of hydride, or you can say stability towards heat. Write the topic. Thermal stability of hydride, or stability towards heat. Hydride, that means LiH, NaH, MgH. I'm going to take the only first group, NaH, KH, RBH, and CSH. So the thermal stability is basically, you can arrange it. Have you arranged it?
No.
So basically here you can see thermal stability depends on MH bond. This depends on MH bond. And the bond which is smaller will have will require most of heat to break it. So the answer will be like this. Okay, so I'm going to write all alkali metals reacts with all alkali metal hydride all alkali metal hydride reacts with water to form metal hydroxide like if we're going to take MH and we are going to keep it in water, it will become MOH plus H2, metal hydroxide and hydrogen gas. You can write. Just write it and let me know if you are finished.
Done.
Write a point. All alkaline earth metal except beryllium combine with dihydrogen upon heating to form their hydride except beryllium. Always remember. So basically this is M and this is H2. It will react with each other and it will form MH2. You know that this is metal from alkaline are the metal. This is hydrogen. Hydrogen has a valency one metal. This metal alkaline are the had a valency that is 2. So the formula will be MH2, right?
Yes.
And we can write Mg plus H2. That will give MgH2, magnesium dihydride. What about BH2, BeH2, beryllium hydride? That is prepared uh, by a special method. I'm going to write it. BeH2 can be prepared. Basically, we are going to heat it, then it will be prepared. Can be prepared by the reaction of beryllium chloride with lithium aluminum hydride. This lithium aluminum hydride will is mostly used in organic chemistry. This is the best reducing agent basically. I'm going to write its name LiLH4, lithium aluminum hydride. Lithium aluminum hydride. Now you can see 2 moles of BeCl2 will react with LiLH4 to give 2 moles of BeH2, LiCl, and then AlCl3. Done.
Done.
Moving to the hydride part. order of thermal stability. TS stand for thermal stability. So basically here it is BeH2, MgH2, CaH2, SrH2, and BaH2. You know that these all are ionic in nature, and this must have more thermal stability, but these are covalent in nature, but they exist in polymeric form. Polymeric hydride. Polymeric hydride. Basically, BH2 covalent, that it will share BHH, and you can see that this central atom has only 4 electrons. To be a stable, any elements needs at least 8 electron to be filled. Its octet should be completed, right? So
Yes.
in order to get stabilized, it exists in polymeric form, and whenever there is polymeric form, their molecular weight increases, and whenever molecular weight increases, van der Waals force of attraction increases in covalent compounds. And if van der Waals force of attraction is high, it is not easy to break it. It is so order of thermal stability will be like this. Just write it.
Done.
Very good. Now moving to the next reactivity, that is reactivity towards oxygen. Reactivity towards oxygen. Oxygen, basically metal reacts with oxygen to form 3 types of oxide. The first one is normal oxide. Normal oxide, that is O minus 2. That means this oxygen needs 2 electron. Whenever oxygen withdraw 2 electron, that is normal oxide. Among alkali metal, lithium forms normal oxide. Normal oxide. That is the formula will be Li2O. The second is peroxide. And here peroxide has a formula O2 minus 2. That means each oxygen will require 1 electron from other element. Peroxide. Among alkali metal, sodium forms peroxide. One sodium can give only 1 electron, so there will be 2 sodium to satisfy it. And the third one, among alkali, third one basically superoxide. Third one is superoxide. And that is O2 minus. That means 2 oxygen required, 1 electron. That means half of it will be divided among alkali metal. Potassium, rubidium, and cesium forms superoxide. That means this alkali metal can only give 1 electron, so they will share with it. MO2. Okay.
Done.
Very good. Why they form different types of oxide, superoxide, monoxide, and normal oxide? Basically, a compounds which formed should be stable. So in order to form different of oxide, they are basically lattice energy compensation. Basically, you know that this O2 will gain an electron to form O2 minus. If it will gain an electron, it will be O2 minus or not.
Yes.
And O2 minus is superoxide.
Yes.
And you know, do you know electron gain enthalpy?
Yes.
The first electron gain enthalpy here will be negative. So I am going to write it delta H negative. Okay. Now again, if you are going to add another electron, there will be repulsion. There will be repulsion. So delta H here will be positive. The delta H here will be positive, and it will be converted into O2 minus 2. And here it is your peroxide, right?
Yes.
And now total electron on this will be 8 to the 16 to 18 electrons, right?
Yes.
Now if you are going to add two more electron, you will need another very more energy. That means if you are going to give energy, delta H will be positive. If you are giving energy to the system, delta H will be positive. If it is releasing energy, that is negative, delta H will be positive. And here it will be 2O minus, because here you can say it is 18 electrons. Then when it will add up plus 2 electron, it will be 20 electron. And whenever oxygen have 20 electrons, bond order will be 0. Do you studied molecular orbital theory? Have you studied it?
Yes.
So bond energy, if 20 electrons are there, that means bond energy equal bond order. This is basically bond order. And if bond order equals to 0, that means there is no bond. So it will break it. It will be broken. The bond will be broken and it will form 2O minus 2. 2O minus 2. Like this. Now you know that Li plus, Na plus, K plus, Rb plus, and Cs plus, which will have highest lattice enthalpy. This Li plus, Na plus, I plus, sorry, K plus, Rb plus, Cs plus, which will have highest bond lattice enthalpy, highest lattice enthalpy.
Yes. Yes.
I'm talking about lattice energy. Lattice energy depends upon the charge, magnitude of charge, and since the magnitude of charge is same, we will go to the size of ions. And how it depends on size of ions? Lattice enthalpy. Inversely proportional
Obviously.
to. So lattice enthalpy, this will have more lattice enthalpy than this, than this, than this, right?
Yes.
Now you see, whenever a compound is formed, the stability of compound should be maximum, or the compound should be stable. And in terms of energy, we can say that the compound should have minimum, the compound must have minimum energy. If the compound has minimum energy, that means it has maximum stability. Actually, stability is inversely proportional to energy, right?
Yes.
So basically how it will to form bond, you can easily relate it. How? Now you see that this is peroxide, this is superoxide, and this is normal oxide. This is normal oxide. Now you can see say that you can see that this will have maximum positive charge, right? Maximum positive charge, not charge. This will have maximum delta H, right? Positive
Yes.
delta H, because in the first step we got some energy released, but in the next step you have to give the energy, and the third step you have to give a lot of energy. So this molecule, this will have maximum delta H positive, right?
Yes.
And now you can see that this is more stable, this has maximum lattice energy, so it will go to combine with this to compensate the energy. Basically here there is positive, here it will be negative, so positive negative will cancel each other, and the compound formed will have minimum energy and maximum stability. Are you getting my point?
Yes.
That's why lithium does not form peroxide as well as superoxide, because here the energy compensation is not good. The best energy compensation between lithium plus and normal oxide is very good. That's why it forms only oxide. In case of sodium, it goes more towards peroxide, because the energy compensation is here, the energy compensation for sodium is good for peroxide, normal not for normal oxide as well as superoxide. So major product, if you have given a question, sodium reacts with oxygen, either it forms peroxide, normal oxide and superoxide. We will take on peroxide because the major product will be peroxide, because it is more stable in peroxide form as compared to normal oxide and superoxide. Are you getting my point?
Yes.
So in the same way, this Ka plus, Rb plus and Cs plus is good for superoxide, not for peroxide and normal oxide. So you can write it. I'm going to write a point about this. Lithium forms normal oxide. Sodium forms peroxide, and remaining alkali metal, that means rubidium, potassium, rubidium, cesium, forms superoxide. It is due to lattice energy effect, or we can say lattice energy compensation. In the same way, it goes for second group.
Done.
So this is basically alkaline earth metal, and this is oxide. Which type of oxide will form? It will form, I'm going to write, beryllium, magnesium, calcium, then strontium, and then barium. This basically normal oxide. Normal oxide, it will form normal oxide, and magnesium will also form normal oxide, but when it comes to calcium, it will be stable in peroxide. This is basically peroxide. When it comes to strontium, it is also peroxide, but when it comes to Ba, it is also peroxide. Just write it. So we can see peroxide, in form of peroxide, how many metals are there? Sodium, hydrogen as well. Hydrogen also exists in the form of hydrogen peroxide, barium, strontium, and calcium. These five are more stable in this form, peroxide form. Are you done with this?
Done.
Okay. Now wait a minute. Just write a topic, a reaction with air. Reaction with air. Air, that means you have to react with O2 as well as N2. Okay.
Okay.
So write with me. Among alkali metal, only lithium forms nitride. That means lithium from the first group, only lithium forms nitride. That means lithium will react with nitrogen. None of other elements will react with nitrogen like potassium, sodium, rubidium, and cesium. Li3n, because of lattice energy effect. So you can write due to lattice energy effect. Okay.
Okay.
It means a smaller size cation forms a stronger bond with a smaller anion, that is n minus 3. Okay, we can also make a list here. Alkali metal, there is lithium, sodium, potassium, rubidium, and cesium. And here is air, that means O2 plus N2 react. So you know that lithium react with oxygen to form Li2O, as well as it can react with nitrogen, it will form Li3N2. Now with sodium, sodium will only react with oxygen, so it will form Na2O2. Potassium, superoxide. Rubidium, superoxide. Cesium, superoxide. Simple. As well as we can write here for alkaline are the metal, and here it is air, that means O2 plus N2. So here is beryllium, magnesium, calcium, strontium, barium. What is here? Beryllium will react with oxygen, so it will form beryllium oxide as well as nitride. In the same way, magnesium will also react MgO plus Mg3N2. What about calcium? Calcium will form two types, oxide as well as peroxide and Ca3N2. This will be minor. This will be minor because the energy compensation here will be not good. Strontium SrO2 peroxide plus Sr3N2. This is nitride. BaO2 plus Ba3N2. In the same way here, oxide of BaO and SrO will be, but this will be minor like CaO, calcium oxide.
Done.
All
Yes.
very good. Reaction with water. The reaction of oxide with water. Reaction of oxide with water. You can see reaction of oxide with water. It will form, since metal oxide is basic in nature, so if you are going to react with water, it will form basic oxide, that is lithium hydroxide, and here only lithium hydroxide. Let me check it. Okay. if we are going to react with peroxide, in the presence of peroxide, sodium hydroxide will form along with H2O2. And if you are going to react with superoxide, then potassium hydroxide will form along with H2O2, and one O2 will be released, molecule of O2.
Done.
Now, write another topic: reaction of nitride with water. Since it is metal, that's why it will give metal hydroxide with NH3 ammonia. So Li3N will react with 3 moles of H2O. So it will give 3 LiOH as well as NH3. In the same way, if you are going to take magnesium Mg3N2 to react with water, it will give MgOH whole twice plus NH3. Just write it.
Done.
Very good. So in the slide, right, reaction with halogen. Reaction with halogen. So when we are talking about halogen, just remember these 3 points are very important for you in class 11th as well as 12th. Fluoride of all S block element, including aluminum, are ionic in nature. Including aluminum are ionic in nature. Lithium, sodium, potassium, rubidium, cesium. Then magnesium, not beryllium. So I'm going to write except BeF2. Magnesium, potassium, magnesium, calcium, strontium, barium. If react with fluorine, the compound formed will be ionic in nature. But this BeF2 is not. Okay. Second point, which is very important, chlorine, either chlorine, bromine, iodine. If it reacts with other than lithium from first group, Na plus, K plus, Rb plus, and cesium plus are ionic in nature. They all are ionic in nature. But if lithium will react with chlorine, bromine, or iodide, then it will be more covalent. Third point is regarding that point that I just told you. Chlorine, bromine, and iodine of Li plus or alkaline earth metal and aluminum, any alkaline earth metal, has more covalent character, according to Pajan's rule.
Done.
Very good. Right. Melting point of halide of S block. Melting point of halide of S block. If it is ionic, you will check, you will get melting point and boiling point directly proportional to lattice energy. If it is ionic, if it is covalent, the one which has more covalent character will have lesser boiling or melting point. Covalent due to more polarization. Basically, they will form ionic compound. We just discover which has more covalent character or which has lesser covalent character. So melting point or boiling point inversely proportional to polarization. So this is the so if I'm going to ask you order of melting point, MP, that is stand for melting point, MF, MCl, MBr, MI. So you have to check covalent character. Can you arrange it? You can see that if I'm going to tell you that just arrange it in order of polarization or covalent character. M is same in all the compound, but when we go for F minus, Cl minus, Br minus, charge is also same. So we go for size. Size of anion is greater, polarizability greater. If polarizability greater, that means covalent character greater. So this has more covalent character. That means this will have lesser melting point, right?
Yes.
So it will be arranged in this. Now LF3, MgF2, and LIF. You have to arrange this. Can you arrange it or I should tell you?
AlF3 has more melting point.
AlF3 has more melting point. Like this.
Yes.
Okay. Why? Because this all are why?
Because the charge is more in aluminum.
The triad is more covalent.
The charge is more.
If the charge is more on cation, that means that will have more polarization power.
Yes.
And if that will have more polarization power, that means lesser melting or boiling point. Polarization power high, covalent character high. Or if it will have more covalent character, that means it will have lesser melting point, right or wrong?
Yes.
Yes. So the answer is wrong. The answer you have given me is wrong, right?
Yes.
But the answer is right. Why? I point that fluorine react with S block of any element except beryllium. That means lithium, sodium, potassium, rubidium, cesium, as well as magnesium, calcium, strontium, barium, as well as aluminum. If all this element separately combined with fluorine and formed a compound, that compound will be ionic in nature, right?
Yes.
And if the compound is ionic, we will go for lattice energy, because boiling or melting point in an ionic compound is directly proportional to lattice energy.
Okay.
Now you will see that here it is L plus 3, here it is Mg plus 2, and here it is Li2. I told you that lattice energy is directly proportional to magnitude of charge, Akifah.
Yes.
So this has more magnitude of charge. It will have it will have more lattice energy. That's why it will have more boiling point or melting point.
Yes.
So I'm going to give you another question which is very important. LiCl, NaCl, KCl, RbCl, CSCl. Are you done with this?
No. LiCl will be covalent.
Very good. LiCl will be covalent. So it will have minimum boiling point,
Yes.
melting point, and NaCl, KCl, RbCl, CSCl. We will ionic, and we will go for lattice energy,
Yes.
and the size which has since the charge is same, we will go for size. Na plus will have lesser size, a smaller size. That means the order will be this.
Yes.
Very good, very good. Can I change the slide?
Yes.
So the last question from this topic: which of the following has lowest boiling point? A. Lii, B. Nai, C. Ki, and D. Rbi. The question is so easy.
Li.
Lii, because this is covalent, this is ionic, this is also ionic, this is also ionic. That's why. Okay.
Okay.
Very good. Can I change the slide?
Yes.
So write a point. All alkaline earth matter comprises with halogen at high temperature except beryllium, because beryllium is prepared with some other methods. Second point, the decomposition of ammonium tetra fluoroberylate, tetrafluoroberylate ion, that means NH4 whole twice BeF4, is best way for the preparation of BeF2. For the preparation of beryllium fluoride. You can see when we heat NH4 whole to BeF4, we get BeF2 plus 2 moles of NH4F. Basically this NH4F, that means the bond between NH4 positive and F minus is ionic bond. So I'm going to write it here. Write with me. Compound of NH4 positive with anion, that is F minus, is ionic. Lots of examples are here. NH4Cl, NH4OH, NH4NO3, etc. Okay.
Mm.
Okay. So Akifah, we are ending our class here.
Okay.
We will start. We will complete this chapter in the next class. Okay.
Okay. Thank you.
Okay. Thank you.